All right, everybody. I think I have a way of making sense of this, which hopefully will make sense to you. So let's just launch into a problem, and I'll kind of explain a way of thinking that I think will apply to all of the problems. So let's say that song lengths of top 40 pop songs are approximately normally distributed with a mean of 2.4 minutes and a standard deviation of 0.33 minutes. So all of the problems are going to be similar, where we're imagining if we were going to actually take a random sample of a bunch of pop songs and then make a histogram, the histogram would have an approximately normal distribution. But we're not actually doing the sample, we're just asserting that we believe that that's the case. And so we can sort of imagine that by sketching a little normal picture. If we don't make this a standard normal curve, then the units of the x-axis are whatever units the mean and standard deviation are in. So here it would be minutes, which is length of the song. So we'd have the mean here at 2.4, and then the standard deviation controls kind of how tightly this hump is happening right at the mean. So 0.33, if we were going to make that smaller, the hump would be kind of taller here. If we were going to make this larger, it means the spread around the mean is larger, and so we would have a kind of more flattened out hump. Two really important things to know is the area under this entire curve is 1, which represents 100% chance that a randomly sampled song will happen somewhere, which means that it will have some song length. The other important thing to know, well, here, let me ask it as a question. What is the probability that a song will be longer than the mean value of 2.4 minutes? So hopefully you know the answer. The answer is 50%. Because that's what it means for the data to be approximately normally distributed. It means that exactly half of the data is larger than the mean and half is smaller than the mean. And that's an experimental question. You know, that's not automatically true of any variable that we might be interested in. But right now we're restricting our attention to variables where we're assuming that if we did, or we're asserting that if we did do this random sampling, then the data would turn out to be symmetric in exactly this way. So in a problem situation, you'd read the question, and if the question was telling you that the data is approximately normally distributed, one way of understanding what that means is that it has this shape, and that 50% is here and 50% is there. So what if we were asking what's the probability that a song is shorter than 1 minute? What we're asking is, what's the area under the normal curve smaller than 1 minute? So we're asking about the shaded region. We want to know how much area is under there. So this is exactly the kind of question where the normal cumulative density function, normal CDF function on your calculator, can help you answer it. So whenever you have a kind of question where the information you have is a boundary value, like 1 minute, and what you want to find is the area under the curve, or the probability of a song having a particular value, or the proportion of songs that have a particular value. All of these three ideas are the same because they all correspond to this shaded area on one side or the other side of the boundary value. So if I wanted to know what proportion of songs have a length of less than 1 minute, that's this area. If I want to know what's the probability that a song has a length less than 1 minute, that's that area. If I want to know what's the probability that a song is more than 1 minute, that would be the area to the right of the boundary value. And so the way that you solve all of these problems is you hit the second key and then hit the vars key, and then you select the normal CDF function, and then it'll pop open a window, and there's 4 different things you can type in the window. You can tell it the lower boundary, the upper boundary, the mean, and the standard deviation. And some people's calculators also have a tail direction, tail to the left or tail to the right, and I'll tell you about that in a second. For this problem, so the normal cumulative density function always finds the area between 2 points. So we're interested in to the left of the boundary value. But this function actually expects us to give 2 boundaries, a lower boundary and an upper boundary. So because we want the entire area to the left, let's set the lower boundary to be something very, very, very small, such as -99999. You might notice in this particular context, maybe it doesn't make sense to have a song length that is negative. But what we're imagining here is that we've fit the actual real data to a normal curve. And so now we're using our normal curve model to give us the probability. So we would still use this kind of farthest possible lower boundary. The upper boundary here is the right-hand side, and so that would be 1. The mean is 2.4, and the standard deviation is 0.33, and those were given in the problem. And so then when you hit return, the number that this gives you is this area, which corresponds to the probability for having a result in that region. Sorry, one last thing. That's assuming the tail is to the left. So let's ask the other question. What's the probability of having a song longer than 1 minute? One way you could do that would be to type this same set of values into the normal CDF function, only select tail right. And then it will tell you this area over here if the tail is right. The other way to do it is you just find the complement of this probability. So 1 minus whatever that value was should give you the rest of it. Sometimes you'll be asked a problem that's kind of like the reverse of the problems we just looked at. So, for example, what if I wanted to exclude the top 10% of longest songs from my playlist that I'm making for my wedding event? What's the longest song I'd want to keep? So in this case, there's some song length, and we don't know what it is. But what we know is that 10% of all songs are going to be longer than that one. And so that's what we're trying to figure out. So maybe you can see now why I said this is the reverse of the last set of problems. Here, what we have is an area, or a probability, or a proportion. And what we want is the boundary value that would have that area, or probability, or proportion. So how do you do it? Just like before, we're going to hit second vars, but this time we're going to use the inv_norm, which stands for inverse normal function. And we have 3 things we tell it in the window that pops up. We tell it what's the area that we're interested in finding the boundary value for. So this is 10%, but you wouldn't actually put 10. You would express it as 0.1 because the area under this entire curve is 1. And so this can't be 10 because that's too big. It would have to be 0.1. And give it the mean and the standard deviation, which is the same as before. Here, because we want the 10% to be to the right of our boundary value, we would say tail is to the right. And not everybody has that option, so I'll show you another thing you can do in just a second. But when you hit return, that will actually tell you what the boundary value is. And right now, we're still working in units of minutes, and so that would be the length of the longest song you'd possibly have, because any longer song would be inside this 10% you're excluding. If your calculator doesn't let you set the tail to be the right, then what that means is the area that you type in here is going to correspond to the area that's to the left of whatever boundary value it's going to find for you. So because we want 10% of the data to be to the right, but we can't solve for that, we're pretending, let's instead find the boundary value where 90% is to the left, because that should be the same thing. So we'd use the second vars, inv_norm, but then the area we're looking for is an area of 0.9 with a mean and standard deviation as before, and then the tail is to the left. But you probably wouldn't see a tail menu. It would just be like automatically to the left. And that number should give you the same value as the one over here. So those are the 2 basic types of problem that you might see. We might have a situation where you know your boundary value and you want to find the area or probability or proportion on either side, or you know what you want that area to be, but you're not sure where the boundary value is that creates that particular area. And so you would do the inv_norm to find that one. Come back in the next video for a little bit of a nuance. Questions S and T from last time involved a variation on these ideas, and so I'll kind of show you how to think about that.